Hello everyone, my name is Purushottam Kumar and I am from GEE 18 batch, and today I am going to discuss something about the PMMC instrument. PMMC, Permanent Magnet Moving Coil Instruments. In the discussion we will see what is the definition of the PMMC instrument, its construction, third is the working principle, its working, and the most important torques and equation involved in the working principle of PMMC instruments. In this we will see what is deflecting torque, controlling torque and damping torque. Then we will move further to the advantages of the PMMC instruments and then the disadvantages of the PMMC instruments. So first of all we will discuss about the definition and the history of the PMMC instrument. The instruments which use the permanent magnet for creating the stationary magnetic field between which the coil moves is known as PMMC instrument. Here we can see that is the U-shaped horseshoe magnet which provides the equal north and south pole to this coil. This is the spindle of the PMMC instrument, this is the pointer, and this is the calibrated scale which shows the approximate or a proportional reading of the input supplied to the PMMC instrument. It is an analog instrument. Analog instruments are those instruments which shows the analogous value on the scale. Now it is developed by the scientist D. Arsenval. Therefore, it is also known as galvanometer and the galvanometer. Its symbol is this one, the U-shaped, and a coil between this. In continuation, now we will discuss something about the construction of the PMMC instruments. Here I had taken the two perspectives of the PMMC instruments, the front view and the top view. Basically, these PMMC instruments are made up of some basic important parts. First one, the coil of the PMMC instrument. It is made up of thin copper wire and it is mounted on aluminum cores or the soft iron core. These are the two permanent magnets between which this coil is mounted. These permanent magnets are made up of some alloys. For example, the alnico. Alnico is the mixture of aluminum, nickel and cobalt. These U-shaped permanent magnets are also made up of strontium iron or samarium cobalt, etc. This coil is pivoted on the jeweled bearings and thus coil is free to rotate. The current is fed to the coil through these spiral springs, which are in two in numbers. We can see that one spring is this and another is this one. The coil this is the coil which carries the current to be measured moves and the strong magnetic fields of these permanent magnets and a pointer. This is the pointer attached on the spindle which shows the measured value. A calibrated scale that we can see here. A calibrated scale and the mirror is also attached for better observation of the reading. Here we can see that this is the balancing weight which further stops the pointer to move indefinitely. So those were the things that we saw on the construction of the PMMC instruments, and now we will discuss about the working principle of the PMMC instruments. These PMMC instruments work on the principle of electrical measurement. When a current carrying conductor is placed in a magnetic field, it experiences a force and tends to move in the direction as per the Fleming's left-hand rule, or in other words, we can say that it follows the method of motoring action. Here, this figure shows the Fleming's left-hand rule. The thumb shows the force or the motion of the pointer. This index finger shows the direction of the magnetic field, which is basically from the north to south one. This, the middle finger, shows the direction of the current. When it is placed accordingly, we can find the motion of that pointer. Now, in continuation, we will see the working of the PMMC instruments. The working of the PMMC instrument is done in the three stages. First, the Lorentz law or the deflecting torque, we can say. Second one is the spring control mechanism. We can also say that the controlling torque. Third one is eddy current damping. In this equation, we can see that these all three forces or the mechanism forms the PMMC instruments. Let's see how it works. When current flows through the coil, it generates a magnetic field which is proportional to the current in case of ammeter that we supplied in the in the PMMC instrument. The deflecting torque is produced by the electromagnetic action of the current in the coil and the magnetic field. We can see that there is a permanent magnet. In the construction we had already seen this, there is a permanent magnet, and when we supply the current or the source voltage to the coil, it also forms the electromagnetic field, isn't it? So both the field, when interacts with each other, it shows the deflection in the pointer which is attached to the spindle. When the deflecting torque and the controlling torque are balanced, the moving coil stops, and its angular deflection represents the amount of current to be measured on the scale calibrated. So what is deflecting and controlling torque here? Here deflecting torque, we had seen that when the two forces, that is two electromagnetic forces, attracts or interacts with each other, it shows the deflection in the coil, but it will move to the infinite position. Here we can see that this is the scale and this is the pointer. If this force will act freely, this pointer will move to the infinite position or the full scale value. But there is a spring control mechanism here which prevents this pointer to move to the infinite position, that is the final value position, and stops to the position where it has to be stopped, that is the value at which it has to be stopped. Let's say if it is 5 ampere or 2 ampere, etc., it will stop to that position, that is it will stop to the position where the approximate or the proportional value of the amount of supply we gave to the instrument. Now the eddy current in the aluminum core acts as damping agent and prevents the oscillation of the pointer. About these all forces, that is the deflecting torque or controlling torque and this one, the damping torque, we will discuss in the further continuation. In this slide, we will see the torques and equations involved in working of PMMC instruments. In this part, I will explain you about the deflecting torque, controlling torque and damping torque. Let's start with the deflecting torque. The force which deflects the needle from its initial position is known as deflecting torque. In the case of PMMC instrument, both the perpendicular forces, that is the field produced in the coil by the current and the field produced by the magnetic field, act simultaneously. Thus, by Lorentz law, we can say that the force experienced by conductor, that is F force, is equal to N into B into I into L. Here N is the number of turns on coil, B is the flux density in air gap, I current in the movable coil, L is the length of the coil. Now the deflecting torque experienced by conductor, here I show it by tau d, is equal to force into perpendicular distance, that is tau d is equal to NB I L into omega W by 2. Here let's see what is W by 2. We know that the conductor of the movable coil is like that something. This is the length of the coil and this is the total width of the coil, W. And the perpendicular distance one is this one, so this part is equal to W by 2. Since there is in the coil there is two conductors, this conductor and this conductor. In one coil there is always a two conductor, we know that. So the force experienced by coil, here we saw that the force experienced in the one conductor. Now the force experienced by coil, that is two conductor, will be twice into N into B I L into omega by 2. When we solve it, it will become deflecting torque in the coil is equal to NBI into A. Here we see that A, what is A? This is the area of the coil. Area is equal to length into width. We know that. This is what about the deflecting torque. Now let's see about the controlling torque. This is a torque produced by the spring action and opposes the deflecting torque so that the pointer comes to at the rest at the point where two torques are equal and to give the accurate reading. When these two torques are equal, that is when TD is equal to TC, this comes to the position where the approximate or the proportional value of current is supplied to the meter. This, let's see here, if the deflecting torque acts freely, it will move to the final value as I had told you earlier. So this torque acts to control the deflection of the pointer so that it comes to the point where it has to measure some value. Here TC, that is the controlling torque, is equal to K theta. Here K is the spring constant, which is in Newton meter per radian, and theta is deflection angle in radians. Here we can see this is the initial position of the pointer and it is moved by some angle, let's see alpha, and this is the deflection angle. It can also move to the here put this position or this position. So from initial to this position, the angle is known as the deflection angle. Okay. At equilibrium, that is the position where deflecting torque is equal to controlling torque. We can say that the NBIA, that is deflecting torque, which we had discussed in the previous slide, is equal to K theta. From this equation, when we solve it, we will see that the theta is equal to NBA upon K into I. This is the current. So we can say that theta is directly proportional to I, or theta is equal to GI, where G is also the constant whose value is NBA into upon K. From here we can say that the theta is directly proportional to I. Here we see that, therefore this is the linear relation. This is a linear relation between the angular displacement and the current. So the instrument is suitable for DC measurement, and also the calibration of the scale will be uniform. Now let's see about the damping torque. This torque ensures the pointer to comes at an equilibrium position, that is at rest in the scale without oscillating, to give an accurate reading. When the deflecting torques and controlling torque simultaneously acts on the pointer comes to at an approximate position. Let's see if it has to measure this one, that is 0, 1, 2, 3, 4 and 5. If say it has to measure this 2 ampere current, when deflecting torque and the controlling torque act, the pointer will comes to this position first and start oscillating to some extent this value. That is, I am going to enlarge it. The pointer will come to this position but it starts to oscillate at this position like this. So if we take the reading, it will be very difficult to take the exact reading what it actually wants to give. So this is a damping torque which opposes this oscillation of the pointer and gives the accurate reading to the observer. Here we have observed that the deflecting torque and controlling torques are unidirectional. That is, the deflecting torque moves to this side and the controlling torque always acts in this side. If there is no deflecting torque, there will be no controlling torque. There is no possibility of controlling torque when there is no deflecting torque, isn't it? And we have also observed that this one damping torque is bidirectional in motion. That is, when the pointer oscillates in both this sinusoidal condition like this acts in both sides. In this PMC instrument, the eddy current damping is used. Now we will see the equivalent circuit of the PMMC instrument. This is the equivalent circuit of the PMC instrument. From here the current goes, this is the indicating part, and this is the RM, which is the internal resistance of the PMC instrument. This is the voltage applied. Okay. With this equivalent circuit we can form the other types of meters also, that is the ammeter or voltmeter, by applying the certain amount of shunt or series resistances. Okay, so let's see about the advantages of the PMC instrument. The first advantage is that it consumes less power and has great accuracy. It gives a perfect reading, that is whatever the amount we want to calculate, it gives the accurate reading. It has uniformly divided scale and cover an arc of 270 degree. We saw that it has linear relationship, that is the angular displacement is linearly proportional to the current. Therefore the scale of this meter is very uniform. So if you want to measure the any value, if there is not mentioned also, so let's see here it is 0, 1, 2, 3 or 4. If you want to say here what is the reading of this, we can measure it that also. Although it is not mentioned what is here, it is not here, that 2.6 it is not given, but we can measure that, isn't it? So this is the advantage of this instrument that we can approximate the value at any point. Third advantage is that it has high torque to weight ratio. Fourth is that it can be modified as ammeter or voltmeter with suitable resistances. I already told that in this equivalent circuit condition. It has efficient damping characteristic and is not affected by stray field. Let's say if there is any type of magnetic field or electromagnetic field and these meters, it is not affected by the this instrument is not affected by those stray magnetic fields. It produces no losses due to hysteresis. In this instrument there is no hysteresis loss, all say, because it measures only small amount of small ranges of the current or voltages, so there is very less, or we can say that there is no hysteresis losses. Now we have come to the very last slide of this PMC instrument, that is the disadvantages of the PMC instrument. So let's start. First one is that it can only be used for DC. Very first disadvantage of that, it can only measure the DC value or the average value, because as the reversal of current, that is the AC current, which is also known as reversal current or alternating current, cause a reversal of torque on the coil. If we give the AC in this type of instrument, it will start oscillating to its value like this. We can say like this from this axis. Second one, it is very delicate and sometimes use a AC circuit with a rectifier. We can say it can also measure the AC value. How it measures AC? Let's see. If the AC value is very small, let's say in few milliamperes or 3 millivolts, it can be used with the rectifier. Rectifier converts the AC into pulsating DC like this one, the half wave rectifier and the full wave rectifier like this. It can measure these type of small values of AC current. Third disadvantage is that it is costly as compared to PMMI instruments. These instruments are costly as compared to the permanent magnet moving iron instrument, because it uses the coil construction, isn't it? Very complicated circuitry, so it is costly. It may show error due to loss of magnetism of permanent magnet, aging or snapping of spring, or due to change in temperature. This is the most unwanted disadvantage of this PMC instrumentation. This instrument gives errors due to when the permanent magnet get aging up. It means if the age of the meter gets over and over, it also gives the false readings. Snapping of the spring, we know that the V gives supply to the spring, which gives the which flows the proportional current in the circuit, and we get the approximate value through the reading through the on the scale. It also, so the snapping of the spring also gives the false in the instrument. And the third one is change in temperature. When the temperature changes, we know that the coil is made of the conducting material, okay, and when the temperature increases, the resistivity of the resistance of that conductor also increases, and its resistance gets changed, and therefore it also shows the different reading or the false reading or somewhat error in the circuit. Error in the meter. The third is and the second last disadvantage, it is not suitable for high range operations. We know that on high ranges of current, if the higher amount of current is flowed through the circuit, it will get heated up, and the temperature disadvantage will occur. If one of the spring of PMC snaps, it will show zero reading, as the circuit of moving coil is done through the spring. Okay, we know that the supply is given to the system, the PMC instrument, through the spring. These are the springs. With these springs, we give the supply to the instrument. If one of the spring gets snapped, it will break the electrical circuit, and it will not give the any reading in the circuit. And last, these springs are made of the phosphor bronze helical shaped springs. These springs are made of the phosphor bronze. So that's all from my side. I hope I had made you understand about the working and all the characteristics of the PMC instruments. Thank you all.